In this video, I want to talk about the systematic approach for solving electric circuits. So this systematic approach provides a mathematical framework to answer this question: how many simultaneous equations we need to solve for any circuit to be considered fully solved. So let's just take a look at this example circuit here. This is the same circuit that I used to go over the important definitions in the previous lecture. So we had the definition of node, essential nodes, branches, essential branches, and so on and so forth. So now in this circuit, considering that all the values for the voltage sources, the two voltage sources that we have, we know the voltages. For this current source, we know the currents, and for the resistors, let's say we all know the values for the resistors, right? So considering this, how many unknowns do we have in this circuit? So let's just go through the unknowns one by one. We have R1, for which we want to know its voltage. So the voltage of R1, the current that goes through R1. So I can assign the voltage in this direction, and I can say the current of R1 is in this direction. What about R2? The same is true for R2 as well. So if I just say the polarity of the voltage is like this one should be R1. And then the current is I of R2. So we need to know VR2 and I of R2. What about R3? So we need to know V of R3, so the voltage across R3, and also the current that goes through R3. And we basically repeat that for all the resistors until we get to R7, for which we want to know what is the voltage across R7 and what is the current that goes through R7. So considering we have 7 resistors, we have 14 unknowns so far. So what else is unknown? The other unknown is the current that goes through voltage source 1. So for voltage source 1, we need to know its current. The same is true for voltage source 2 as well. We need to know its current too. So let's just assign this direction from bottom to top. So this is the current that goes through V2. So is that all? Or is there anything missing? So the other unknown that we want to know is what is the voltage across this current source. So that is another unknown. So for the current source I, we need to know the voltage across it. So considering all of these, in total we have 17 unknowns in this circuit that we want to know for us to consider this circuit to be solved. So does having 17 unknowns automatically translate to the need to solving 17 simultaneous equations? So from the previous lectures, you should know that it is not necessary for us to come up with both voltage and the current of the resistors by doing simultaneous solution of the equation, the linear equations. So if we know, for example, the voltage, we can simply use the Ohm's law to come up with the current. Or we can, if we know the current, again we can use the Ohm's law to come up with the voltage. So you remember, voltage for the resistor was the resistance multiplied by the current. So that was the Ohm's law. So because of that, the number of equations that we need to solve simultaneously gets reduced. Is there any other thing that we can reduce from the equations? Again, we know from previous lectures that if we have elements that are connected in series, the current that goes through them is exactly the same. So that means that the current that goes through V1 is exactly the same as the current that goes through R1. Why? Because they are connected in series. So out of IR1 and IV1, we only need to know one of them, right? The same is true for the current that goes through R2 and R3. It is the same because they are in series. It is the same for the current that goes through V2 and R4 too. They are in series, so if only we know one of them, that's enough for us. So doing this, we can reduce the number of equations that we need to solve simultaneously. What else? Another simplification that we can make is that when we have components that are connected in parallel, we know that their voltages is exactly the same. So that can help us reduce the number of unknowns as well. So for example, we have R7 to be fully in parallel with this independent current source. So that means that if we know the voltage across one of them, we know the voltage across both of them, right? So now, these are the things based on what we knew from before. So let's just see how the systematic approach tries to answer these questions. So the number of unknown currents in the circuit equals the number of branches. We call this number B here. So where the current is not known. So in this circuit, we have 10 branches in total. We have 7 resistors and we have 3 independent sources. So overall, the number of branches that we have in this circuit is going to be 10. So 7 resistors plus 3 independent sources, so 10. So out of these 10 branches or elements, how many of them have unknown currents? The answer to that is 9, because this branch, this independent current source, we already know its current, right? It is I. So that reduces the number of simultaneous equations by 1. So for us to be able to solve this circuit based on the systematic approach, we must have B independent equations to solve a circuit with B branches with unknown currents. So for us here, we have in total 10 branches, but out of these 10, 9 of them are unknown and 1 is known. So for us here, the value for B is 9, because we have 9 branches with unknown currents. So we need to have 9 simultaneous equations to be able to solve this circuit based on the first assumption that we have, which is finding all the unknown currents for all the branches in the circuit. So how can we come up with those 9 equations? The answer to that is, how many nodes do we have? Based on the nodes that we have, we can write the KCL, the Kirchhoff's current law, for each one of these nodes individually, and use those as part of the equations that we want to solve. So how many nodes do we have here? We have A, B, C, D, E, F, G. So in total we have 7 nodes. So out of the 9 equations that we want to have, 9 equations in total that we need to have, we have 7 nodes that we can use for writing KCL. But are all of these nodes useful for us? If you remember from before, we said that if we are in a circuit which has n nodes, only we can write n minus 1 independent equations. So out of these 7 nodes, we can use 6 of the nodes as independent equations. So we needed 9 equations. We have 6. What is left? We need to have 3 more equations. So how do we come up with those? We can use KVL or Kirchhoff's voltage law in the loops of the circuit. So generally speaking, if we have n nodes in the circuit, we can derive n minus 1 independent equations by using Kirchhoff's current law. So here, since we have 7 nodes, we can write 6 independent equations based on the KCL. So now, the final step would be to come up with the remaining equations that we need. So the remaining b minus n minus 1, so for our example 9 minus 6 or 3 equations can be found by applying Kirchhoff's voltage law to loops and meshes in the circuit. So let's just summarize the systematic approach. So first of all, we have b independent equations to solve. Why? Because we have b number of branches with unknown circuits in our with unknown currents in our circuit. Out of these b independent equations that we need, n minus 1 of them is derived by applying KCL to the nodes that we have in the circuit. So out of the n node that we can have in the circuit, we can derive n minus 1 independent equations by applying KCL. And the remaining b minus n minus 1 equations are found by applying Kirchhoff's voltage law to loops and meshes. So that is the basic systematic approach. So now the question becomes, do we need to have or do we need to know all the branch currents? So for example, if we have current I of V1 going through the voltage source V1 and we have I of R1 going through the resistor R1, do we need to know both of these? So the answer to that is no. Why? Because since these two are in series, the current that goes through them is equal. So knowing only one of them is enough for us. So in general, the number of essential nodes is less than or equal to the number of nodes in a circuit. Also, the number of essential branches is less than or equal to the number of branches. So now the definition that we had before for the nodes versus essential nodes and for the branches versus essential branches makes more sense. So for example, here we have this node that is a regular node, right? It is not an essential node. If we apply KCL to this node, the conclusion that we get is that the current that goes through V1 is the same as the current that goes through R1. So that is not something I would say, that needs to be included in our simultaneous equations, right? Because this is something that can be very obvious. The same is true for this one too. For example, node D, that is between R2 and R3, the current that goes through R2 is the same as the current that goes through R3, right? So if we know only one of the two, we basically know both of them. So because of this, we can modify the systematic approach, the initial systematic approach, to not work with nodes and branches, but instead work with the essential nodes and essential branches. So to make it more convenient for us to solve, we use essential nodes and essential branches when analyzing a circuit, since that generally results in fewer number of equations that need to be solved simultaneously. So the updated version of the systematic approach is like this. So for a circuit with B subscript E essential branches, so pay attention to this. This needs to be essential branch. So when we have BE essential branches in our circuit with unknown currents, we need to have BE number of independent equations to solve it. So for the first step, to come up with this BE number of equations, first we find the essential nodes. So let's say we have an E number of essential nodes. So out of these NE number of essential nodes, we need to come up with an E-1 independent equations that can be derived by using Kirchhoff's current law, or KCL. The remaining BE minus N-1 equations can be found by applying Kirchhoff's voltage law, or KVL, to loops and meshes. So up to this point, all I did was give you some dry explanations of this systematic approach. Let's just see how it works in practice. Let's just take a look at this circuit, and of course I'm going to be using this modified version of the systematic approach, not the original version. So in this circuit that we have 7 resistors and 3 independent sources. So how many branches do we have in this circuit? So branches, you remember from before, are basically elements. How many elements do we have? So in this circuit we have 10 branches. But out of those 10, how many of them are essential branches? So V1, R1, the combination is an essential branch. So that's 1. R2, R3 is an essential branch. That's 2. V2, R4 is an essential branch. That's 3. Then we have R5, an essential branch. That's 4. R6, an essential branch. That's 5. R7, an essential branch. That's 6. And we have this independent current source as an essential branch. That's 7. So in total, we have 7 essential branches in this circuit. You remember, essential branches were the path that connect two essential nodes. So the essential nodes that we have here, basically nodes that are the point of contact of more than 3 or more components, are B, C, E, G. So this is one essential branch, the combination of V1 and R1. This is another one. This is another one. This R5 is an essential branch. This R6 is an essential branch. R7 is an essential branch, and this independent current source is another essential branch too. So overall we have 7 essential branches. So out of these 7, how many of them have unknown currents? Only 6, because this essential branch that contains this independent current source has a known current value. It's a current source, right? So we know it's current. So we have 6 essential branches with unknown currents. So that means that our B subscript E is going to be 6. So to solve this circuit, we need to have 6 linear equations to be solved simultaneously for us to be able to say we have solved this circuit. So how can we come up with these equations? The answer is, at first we need to find out the essential nodes and then write the KCL for each one of these essential nodes. So the essential nodes are B, C, E, G, as I said before. And for each one of them, I'm gonna write down the KCL equation. So for B, node B, we have I1 entering the node, so we have negative I1. We have I2 leaving the node, so I use a positive sign for that, I2. We have I6 leaving the node, so we have I6. And finally we have I entering the node, so we have negative I equals 0. So this one is KCL for node B. What about node C? For node C, we have I1 leaving the node, so we have positive I1. We have I3 entering, so negative I3. We have I5 also entering, so negative I5 equals 0. What about node E? For node E, we have I2 entering the node, so we have negative I2. We have I3 leaving the node, so we have positive I3. And finally we have I4 leaving, so we have positive I4 equals 0. And finally, let's just write the equation for node G. So we have I5 leaving, so we have I5 with positive sign. We have I4 entering, so we have negative I4. We have I6 entering, so we have negative I6. And then finally we have this I independent current source leaving, so we have plus I equals 0. So we have 4 equations. But are all of them useful? Are all of them independent? The answer to that is no, because any one of these equations can be created by a linear operation of the other 3, right? So because of that, only 3 of them are independent. So it doesn't matter which set of 3 you choose. So any set of 3 works fine, right? You cannot use 4 of them, but you can choose any 3 of them to use for your calculation. So 3 of these equations would go toward the 6 equations that we need to have. So for now, I'm gonna use these 3 equations. So this one is for node B. This one I1, I3, I5. This one is for node C. So this is node B. This one is for node C. And finally, I3, I4, I2. This one is for node E. So I didn't use the equation, the KCL equation for node G. So only 3 of them. So out of the 6 equations that we need, we have now 3 of them. What should we do about the other 3? The answer to that is we write KVL for the meshes of the circuit. So which one of these meshes we need to choose? So we have, let's say, this one, we have this one, we have this one, and also we have this one. So out of the 4 meshes that we have, which one of them we cannot use? The mesh that includes this independent current source we cannot use, because if you remember from before, we said that for current sources we don't know their voltage, we don't know the voltage across them until everything in the circuit is solved. So because of that we cannot use this mesh. But the other 3 we can use it. For the voltage sources, what we don't know is that we don't know their current, right? Until everything else in the circuit is solved. So now that we know this, let's just write down the KVL for each one of these meshes that we have in the circuit. So let's just call this mesh 1, I call this one mesh 2, and this one mesh 3. So for mesh 1, if I start from node C, I have negative V1 because I'm entering this voltage source from negative side. Then following the passive sign convention, when I have a current that goes through a resistor, I consider this side to be positive, this side to be negative, so this is VR1. And I automatically write the VR1 in terms of the current I1 multiplied by R1, right? So it's going to be I1, R1. Then I get to R5. The voltage across it is going to be I2, R5. Then I get to R3. So I3, R3. And finally, we have I3, R2. This equals 0. So that is the equation for this mesh. What about this one? We have negative V2. So since the current for R2 and R3 comes from right to the left, but we are going the opposite way in our mesh, I use a negative sign for the current here now. So we have negative I3, I multiplied by R2 plus R3. I could do it in the above line too, because these two are in series, so the equivalent resistance is the sum of the two. And then I get to R6. Again, the positive is here, the negative here. So for these ones, the positive was here, negative here, positive, negative. That's why we have this negative sign. We have plus I4 multiplied by R6. And finally, we have plus I5 multiplied by I4 equals 0. So this one was for the KVL for the first mesh. This one is for the second mesh. And finally, for the third mesh, let me just start from point B. We have our I2, R5 plus I4, R6 plus, so here is positive, here is negative. So since I'm going from this direction, let's just follow the approach that I was doing before, so you're not confused. So I go through the same direction that I specified here. So I start from E and then go clockwise. So positive, negative. So ignore the last line that I wrote and I deleted. So if I start from E, I'm entering this resistor from its negative side, again following the passive sign convention. So we have negative I2 R5 and then positive I6 R7 and then negative I4 R6 equals 0. So I can rewrite the first version that I wanted to write also. So the first version was I2 R5 plus I4 R6 minus I6 R7 equals 0. So as you can see, between this one and this one, the only difference is that I have a negative sign multiplied to both sides of the equation, right? So even if I write it like this, that should be fine. If you remember from linear algebra or your math courses, that if you are solving a linear system, it doesn't matter if you multiply one of the equations or even all of the equations by a negative sign on the both sides of the equal sign, right? It doesn't change the answer. So now we have these equations. So we had 3 equations from the application of KCL onto the essential nodes. Now we have 3 equations for the application of KVL onto the meshes. So out of the 6 equations that we required, we now have all of them. So now we can use the concept from linear algebra to solve those equations. So these are the equations, the same equations but written a bit nicer. And finally, when we rearrange these equations, we have this set of 6 equations that we can use to solve the circuit. Of course, you can rewrite this in a matrix form as well. So let's say if I want to write it in a matrix form, I have -1 here, and then 1 here, and then 0, 0, 0, and then 1. I have 1 here, 0 here, -1, 0, -1, and then 0 here. For the third row, we have 0, -1, 1, 1, 0, 0. For the fourth row, we have R1, we have R5, we have R2 plus R3, we have 0, and then we have 0. For the fifth row, we have 0, 0, negative R2 plus R3 for this element of the matrix, then R6, then R4, and then 0. And finally we have 0, negative R5, 0, negative R6, 0, and then R7. So this is getting multiplied by this column vector, I1, I2, I3, I4, I5, and I6. And this equals I, 0, 0, V1, V2, and then 0. Or this is equivalent to having this 6 by 6 matrix of A multiplied by this matrix of X to get the result of matrix of Y. So this is the same set of equations in matrix form. So now let's just summarize. So without any simplifications, how many unknowns did we have? So we had 7 resistors for which we wanted to know both voltage and current. So that is 14 unknowns. Also for the 2 voltage sources, we wanted to know the current for both of them. So that makes it 17. And finally for this one, this independent current source, we wanted to know its voltage. So in total, we had 17 unknowns. So now, considering only one unknown variable for each resistor, either current or voltage, how many unknown did we have? So we had 7 resistors. If we only needed to know their current or voltage, that reduces 7 of the equations. So we have 10 unknowns now. Then, considering similar current variables for elements that are in series, how many now? So we have this V1 and R1 to be in series. So that reduces one of the equations. Then we have V2 and R4 to be in series. So their currents are the same. So that reduces another equation. We have R2 and R3 to be in series too. So that reduces another of the equations. So considering these, we needed to have 7 equations. And finally, considering similar voltage variables for elements that are in parallel, how many now? So since we only have R7 and this independent current source I to be in parallel, so they have both the same voltage across them. So we need to only solve one variable for that. So that reduces the total number of equations that we had to 6. So now the question becomes, is solving 6 equations to solve this circuit a good or reasonable number, or is it still too much? So you know that solving a 3x3 linear system is something that you can do at least like on a piece of paper. When it gets like 4x4, 5x5, 6x6, it's not even possible to do it on a piece of paper, right? So you definitely need to have a good calculator or a computer to be able to solve it. So what if I tell you that even 6 equations to solve this circuit is too much? What if I tell you that you can do it using only 3 equations? So to get to that point, we need to define different variables for our circuit. So 6 equations for solving that circuit is too many. Of course, it's not as many as we initially started. So we started with saying we needed to have 17 equations. But now we got it down to 6, right? So that's so much reduction in terms of calculations that we need to have. But as I said, it can be even less. So the answer is that we need to define new variables for the circuit. So instead of using voltages and currents of individual elements, we need to define voltages of nodes and currents of meshes to be able to even reduce this number of equations for the circuit that we have. So let me just repeat it again. We need to define new variables, namely node voltages and mesh currents, not voltages and currents of individual elements. That helps us significantly reduce the number of equations that we need to have for solving electric circuits. And that will be the topic that I'm going to cover over the next lectures. So here in this video, we wanted to answer this very basic question: how many unknowns do we have in the circuit? And based on the number of unknowns, how many simultaneous equations we needed to solve? Then we went into several steps of designing a systematic approach that helps us significantly reduce the number of equations that we needed to have in order to be able to solve electric circuits. But as I said, that is still not enough. So in the next lectures, I will go over more advanced techniques, namely node voltage and mesh current method, to be able to solve electric circuits more efficiently and much better.